And this was January.
That's prescient almost.
Yeah.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. Your host today, it's me, Marissa Lowe, joined by John Pernay-Fisher.
Hello.
Tom Harvey.
Hello.
Elliot Carter.
Hello.
And our guest today is Divya Persaud.
Hi.
How are you doing today?
I'm good, thank you. How are you?
Good, yeah, very nice to have you on. So Divya, you are a Martian geomorphologist, I believe.
I am a weird mix of professions, so whatever you would like to call me, sure. So my PhD is in image processing, but also 3D visualization, but also a mix of different aspects of Mars geology, and then my background is a mix of planetary geophysics, so studying everything from meteorites and using magnetometers to study inclusions in them, to looking at the icy moons of Saturn in 3D, and also designing a radar mission for Mars. So a pretty wide background. So I don't know quite what hole I fit as a weirdly shaped peg, but sure, I'm a Mars geo.
You're based down at Mullard's Space Laboratory at the moment.
Yes. So that's the Department of Space and Climate Physics at UCL, and we're out in the absolute middle of nowhere in the Surrey Hills. It's a really beautiful spot. And
it is lovely countryside around there,
yes,
isn't it?
Yes, it's nice.
Fantastic. So would you mind telling us a bit of background on your PhD project then?
Yeah, so the background of my PhD is pretty much the problem of being able to study the surface of Mars in a way that is intuitive for geologists and can be helpful for planning rover missions. So currently with Mars data, we have such a great amount of Mars data compared to other bodies, including Earth. And this is fantastic, but it's also a bit problematic because most of that data is remote sensing data, which means it's 2D, it's looking at the ground in map view. With respect to cameras, so I'm in the imaging group at Mullard, these cameras are in different resolutions. They're using different sort of frameworks of reference for the surface of Mars. So there's the sort of dual problem of, okay, how do we turn that data into something that's useful for geologists like me? And the second thing is, how do we make sure that all these data sets sort of agree with each other? And so one way to do that is through 3D. So 3D is fantastic, not just because it's visually spectacular, but also it means that if we use special software, we can use 3D images and rotate them into perspective, use geology tools depending on the software, and actually treat our data as if it's a field, which seems sometimes trivial when you think about planetary science being maybe a field of about 60 years old, when people are sort of used to doing things in the mapping two-dimensional way. But when you think about the number of adjustments that we have to make as scientists to be able to look at a 2D map view of a tiny region in Mars in one resolution and compare it to a larger region in a lower resolution and actually try to figure out complex geology, especially preparing for space missions, that's actually really difficult. So we want to make it as easy as possible and also as intuitive as possible for us as geologists who train out in the field, who are human beings who see on the ground towards the horizon and not, space creatures looking down at the surface of a planet. And so that's taken me in my PhD through image processing of data sets, remote sensing data sets of Mars, to make 3D models of my own. So learning a lot of different software techniques. So I'm not a computer scientist, so I'm really taking this from the geologist point of view. And making the 3D products that I want, stitching them together, and also making sure that they agree with each other across resolutions so that we can get these really nice focused high resolution areas and then the broader context. And from there, I take those products and then visualize them, figure out best ways to visualize them for different purposes. So whether it's kind of first order geological measurements or whether it's science communication, and what works and what doesn't work in that regard. And also using 3D visualization to assess the quality of 3D products, because again, when you're actually in an intuitive environment, you might actually catch things that are wrong when it looks like it's the world around you than when you're looking at it in a sort of sterile map view in GIS software. And then from there, which is the last part of my PhD, is actually taking geological measurements. So that's using a rover mission tool that's being developed for the ExoMars mission PanCam instrument, and using orbital data in that and actually taking measurements of exposed layers at the Curiosity landing site. And so that's a bit more of a stratigraphy exercise in seeing how can we perform the types of analyses that people are doing with rover images, 2D and 3D, but using orbital data in 3D, which is actually really cool, but also really difficult. So that's the general scope of my PhD, and something that I've tacked on a little bit, because the more I do visualization and the more I talk about my science and communicate it, the more I realize that there's so much potential to do outreach in a really meaningful way. Because again, it's almost tactile and tangible, the way we see the Mars surface come alive in 3D. It's really something special, and we can get lost in the data value of it or whatever. But when you show a kid, you know, what's behind me is a giant river channel on Mars. You show anyone that and they think, wow, that looks familiar, or wow, I can imagine myself there. And I think that's really powerful. So sort of a tacked on project to my PhD is figuring out what does and does not work with engaging kids of various ages using 3D. So I've adapted one of my research projects that I kind of archived into an activity for children, which has been really fantastic. And they're so much better at it than me, which is really cool. And like, honestly, a very interesting result, probably from a psychology point of view, which I'm not qualified to do. But just thinking about, okay, how can we actually take what we do and make it really easily consumed by kids and teach them spatial reasoning and about planetary science and about how images are taken. There's so much rich information in interacting with 3D data sets. So there's so much potential there. So I'm trying not to get too carried away with that because I'm writing up, but that's definitely an interest.
Really cool, though. I guess as humans, we're probably almost like hardwired to sort of view things from certain vantage points, and being able to sort of emulate that feeling of being on a surf somewhere else is probably
right.
so significant.
Yeah, so I keep looking at the image behind you, right? Like all those Apollo missions that we immediately resonate with because we see it and we think, wow, that's a horizon of a different body.
Yeah.
And there's a foreground and there's and then you think about how much Mars data we have and we communicate with it in 2D, and it's really impactful that way. But just the capacity to spin it on its head and actually put someone on the ground, I think is really important. And
well, it's so powerful.
It's really exciting. Yeah.
I mean, as you say, like the potential of doing proper field geology is tremendous, really. I mean, So, I mean, how much of Mars are you trying to do this with, or are you focusing on some specific areas, or are you just doing as much as you can get your hands on in terms of data?
I think it would take longer than my PhD to do as much as possible. So I'm only focusing on Gale Crater, which is Curiosity rover's landing site. And so with 2 different cameras, I have full mosaics of the entire crater, which is about 160 kilometers across. And then I've also used high resolution data from the University of Arizona. So that's HiRISE.
HiRISE, yeah.
Yes.
I think we mentioned that a few weeks ago in another podcast.
Cool.
Phenomenal images. Yeah.
Yes. Oh, just amazing, and such a pleasure to work with. So I haven't processed those into 3D data because that's just another entire can of worms when it comes to image processing. But I've chosen just one focus area, which is this really enormous behind me channel cross-cutting the central mound of the crater.
Yeah, I mean, that's so cool. What's the resolution HiRISE again?
The HiRISE is 25 centimeters per pixel.
Right, yeah, I mean, that's amazing, isn't it?
Yes, and so the 3D models are about 1 meter, which is, again, just incredible. Yeah.
So would you mind talking us through how you get from those 2D images to something like the image behind you?
Yeah, sure. So something that is just incredible to me, again, coming from a geologist point of view. So a lot of image processing came from studying human cognition and vision. So when we think about how our eyes or even our ears resolve 3 dimensions, it's because we have 2 ears and we have 2 eyes, right? And they're separated by a certain baseline. And that means that any object that we focus on is seen from a slightly different angle between our eyes. And so that's sort of the first principle of 3D image processing, where we have 2 images, and we can call them stereo images, covering the same data or information, providing slightly different information. And then our brains are able to use that information as well as other information about our understanding of how, for example, sunlight works, and our awareness of our surroundings. And combining that with the images that we see, we can resolve things in 3 dimensions and gain depth. So a computer can do similar things. So stereo matching algorithms and just generally photogrammetry software packages can, if you give them a stereo pair, so stereo images, 2 images either taken on the ground or taken in map view, covering the same area, and those images are encoded with the camera information, which means the camera optics and also where the camera approximately is when it's pointing. So for space, where it is in space, its exact coordinates and its pointing and the angle of the sun. It is able to solve for matching the images and also solve for the 3rd dimension. So it's pretty cool. It's very difficult to do. So I use automated sequences to do this. So it's 2 in-house software based on a product from JPL called Vicar. And then another suite called the AIM Stereo Pipeline from the United States Geological Survey. And these are really great packages that can essentially take your 2 images taken from orbit, extract all the information it needs, and do calibrations, do all sorts of magic, and essentially spit out a 3D product. So the 3D product is usually, so if you think about a 3D object just in space, say like this pen, if you can see that, we can represent it as a surface draped on a whole host of 3D points if we want to play with physics, right? So if you're solving between 2 images, you're going to get the solutions as points in 3D space, and that's called a point cloud. And then from the point cloud, the algorithms can then interpolate them over a grid of your choosing. So for example, for high rise, I mentioned those are 25 centimeter per pixel images, but they can't give out a 25 centimeter per pixel terrain model for a whole host of reasons. But if you tell it, I want a 1 meter grid, then it's going to take each of those points and interpolate it across a cube, right? And of that spacing that you've chosen. And so when in the end, hopefully you get a nice smooth model, if that makes sense, right? So, and that's with my limited understanding of quite how stereo matching works. So I'm able to just give these software packages the images that I want, tell them where I want them to be saved. There's some parameters that I choose, like stereo matching parameters. That's kind of where the science happens, the experimentation. And then in the end, I get a nice TIFF, and I can put that in a mapping suite, like ArcGIS or any other geographic information system. It displays it nice in 2D, but it understands that color values relate to elevation. So you can do science actually in the 2D and get the 3D information. And then from there, with just a little bit of more processing, you can throw it into visualization software that understands the 3D aspect, and you can drape the 2D image on top so it looks realistic. And that's kind of where the magic happens for me. So this is my data set. So this is in a software called NASA Dirt, which is a really fantastic tool to visualize 3D data. So this is in Gale Crater, Mars. So it is about 2 kilometers away from where Curiosity is right now. And so now you can see all these really fantastic layers as we're flying over that are exposed in 3D.
That's
Especially
amazing.
here. Just incredible. Yeah.
How big are these things?
So this is a great view to show you. This is about 2.4 kilometers across.
Okay, so like a normal valley kind of one.
Yeah, this is about 120 meters tall, I would say. This cliff right here. And this is one of my study areas where all these layers are really, really clearly shown, especially in these almost repeating packages that could
that's fantastic,
some sort
isn't
of repeating process. Yeah.
So how much of a role do these 3D images play when people are planning different missions, say rover missions?
They play a pretty huge role. So, and an ongoing role as well. So once for a rover, you constrain the landing ellipse. So this is the general area where the rover is statistically highest to land, which sounds just absolutely bananas when you think about landing a spacecraft. You want to know where it lands, but that's the point. You want to know where it lands, and so you really want a detailed map of the area, geological map in 2D, but also the 3D. And this can help with preparing the science team ahead of time, and also with the early campaign to figure out where the rover is, because it's not so simple. And this is something I've kind of worked on. When a rover lands in somewhere sort of dusty and you sort of see topography in the distance, that's not easy to find. And not always can you actually directly image the rover from these satellite images. So 3D is actually really useful when you visualize 2D data in 3D and actually try to figure out what features might match what a rover has taken in its images. So this is something our group has worked on with rover localization, sort of after the fact, but trying to automatically detect features in rover images, which again are taken on the ground, looking at the horizon, and match them with 2D orbital images, which need a 3D component to really actually generate that horizontal view. So that's, different people do it different ways, different agencies do it different ways, but generally everyone uses 3D in some aspect to do that. And then going from there, scientists still have to think about the geology that a rover will encounter to help inform decision making, which can be actually really difficult when you have 5 different people saying, I want to look at that rock, and they're all different rocks. And you have to think about, okay, what's the triage of our interests and why, and how does that relate to mission goals? So if you are able to really in detail continue to map up traverse, for example, then you can make much more informed decisions about what you're going to study, and also hazards, which are really important.
It's amazing. Yeah. It sounds like a strange game of hide and seek.
Yes, yeah. Definitely.
Are there any, because I mean, the models look fantastic. Are there any instances where you've found anything interesting that kind of hasn't been seen as well in the 2D data and that the 3D really emphasizes?
Yeah, I think in my study area for sure. So if you see behind me, this is my study area. It's kind of hard to say. So much of Gale Crater has been studied in great detail. And so this channel has been of interest for a while because it exposes a lot of layers in this mountain going down to 250 meters and in brilliant detail on the high rise. So there's a lot you can do in 2D with that, but actually from the 3D model, these layers come alive in 3 dimensions, and there's actually topographic relief. And so you can get true outcrops if you visualize in 3D, where, you know, from 2D, you can take sort of a 1.5 dimension outcrop measurement, but you might not be able to go literally around a feature and trace out these layers. So that's something that's been exciting with this. So I don't know if you can sort of see. So say this feature on the floor of the channel, which is like light colored, there's actually a huge amount of relief there. So the thickness of that can be measured really well. And those layers, I'm losing my hand here. See those layers on the far wall that are dark and light? most
Yeah.
of those are actually, if you look at the profile of the channel, are actually like have relief. So that means we can measure thicknesses in a higher precision, and also think about the erosional profile. So there's a lot to be gained from the 3D, and I think it's hard for me to say like I've discovered anything unique. It's more like 3D will always give something unique, and it will also present unique problems, which is just science, I think. So yeah.
That is so cool. It's because I am actually using photogrammetry as well as part of my project, but I'm using it to look at sample exteriors for meteorites recovered from Antarctica, and it's amazing that it can pick up like even the crackled fusion crust and everything is all still there, and it's I can totally see why you say it's such a powerful outreach tool, because these things are so inaccessible for most of the time.
Yes.
I mean, you know, stuff on Mars even more so, because you literally couldn't hold it if you wanted to. But
Is there like the potential to maybe like bring citizen science, that kind of thing into this, of like plonking down members of the public and just seeing if people spot?
Definitely, yeah. I don't know. I bet someone out there is thinking about it. It's something that I've thought about a little bit. So the outreach project that I've done was kind of in this regard. So the children that I worked with were just sort of scouts who visited the lab. But then I started thinking there's actually something interesting that could be done here, where I had an exchange student come from Kyoto, and it was mostly an experiment in learning about physics across a language barrier. But I gave him the same data set and the same game, but I added a bit more detail and said, you know, can you make some quantitative observations here and compare things with published NASA data? And we got some really interesting results. So I'll just walk you through the game. So I'll share my screen if possible.
And for anyone listening on iTunes and Spotify, we'd encourage you to watch the YouTube video that accompanies this.
So this is the game that I did. So this was, I mentioned that I worked a bit in localization. So the project that I originally did was comparing, sorry, this is so disorganized. Comparing rover images with simulated rover images from 2D data that has been mapped into 3D. And so the idea was that our group has developed this method of super resolution to enhance high-rise images. So I was comparing standard resolution, super resolution, and rover images just to see if this was acting as a bridge between orbital data and rover data. So I used this software that allows you to drop a camera anywhere on the surface and then simulate a rover view. So this is the 2D map. Here's the camera, and then here's the camera view. And then here's just like a 3D perspective view of what the camera is generally looking at. So this was fantastic because even just as an exercise to see simulated rover views, where you can see, for example, these ripples on the ground of this crater and their orientations and the outcrops in the foreground compared with the rover image, and also, I guess, yeah, the super resolution bridging. But I saw a lot of potential just in having this camera tool. So I was thinking, you know, why limit this to science? So here's a game that I made, actually just sort of on the fly before a scout's visit at the lab, where I took my project and I drew this sort of freehand traverse of Opportunity Rover. So this was an Opportunity Rover study site in its early days. So I drew this by hand, and then I added a few landmarks. And I gave them a document of rover images labeled by Sol. So Sol is the number of days into a Mars mission at which the image has been taken. And so I said, okay, so, you know, there's a bit of spatial reasoning for the kids, right? So if this is Sol 999, then I give them Sol 1021, they have to think, oh, then it should be around here, and where would it be pointing, and that sort of thing. So they had to actually figure out where the rover images were taken using this 3D data compared with the rover images, which is a lot to explain to kids, but they pick it up really fast. And they pick it up so much more quickly than if you just show them a sort of static 2D image, right? So I did this first with a group of 10 to 12-year-olds. It was about 20 of them split up into groups. And then I started doing it for all these scouts visits at the lab because we got tons of requests to come back from local troops. And then I started doing it for older students. So we had a group of year 12 students come for something completely different. We ran out of time with our project, or we had extra time with our project. So I just said, oh, let's just run this. And they were so much slower at it than the younger kids, which was just amazing. And then I had a couple of kids come to the lab one-on-one. One was 8 and one was 9, and I gave this to them, and they were, they did it in 3 minutes. They would do like 5 rover images in about 3 minutes. And I took about a whole weekend to do it before a conference. So very humbling, but also actually really powerful. And then this is talking about my student from Kyoto, who was doing something similar, except he was actually looking at, okay, once you've planted the camera in the ground and decided that's where the image was taken, what does that camera location look like compared to the NASA location quantitatively, as I mentioned? So he mapped out, this is modified from his maps, he mapped out all the locations and their viewing angles. And then he also mapped out their locations compared with NASA, which is a bit distressing, I think. But so the green is NASA and the red is from our work. So sometimes it's up to 100 meters off, for example, here. There are a lot of reasons why, mostly because there are strong features when you look across the crater and see these really sharp outcrops. And so it's really easy to have error along that direction, because if you're closer or further away, it really doesn't make a difference in what you're seeing. But if you're going in the other direction horizontally, then your angle is changing, right? So if it's looking out at an outcrop, most of the error between us and NASA was in the direction that actually wouldn't change the view. Which means that we probably also have errors. So there were a lot of lessons there about, okay, how accurate is localization? And this was something that was done over 3 days with someone who was just learning English, who was brilliant at physics. So it was definitely a lesson in, okay, where do we go from here? And can we just give this to people to do? Because there's something intuitive about it that people can connect with, that doesn't need too much expert knowledge, if any. And, say we give a 3D data set for Curiosity or the next Mars rovers and say, like, find the rover and give it to 100 people. That might actually be really effective. Whether that's something that can be done or will be done, I don't know. But it's definitely something I've been thinking about quite a lot for the past couple of years.
So I know that you're organising an online conference at the moment, Space Science in Context. Would you mind telling us a bit about it?
Sure, yeah. So Space Science in Context, also known as My Child currently, is an upcoming virtual conference bringing together science and technology studies scholars with planetary scientists and space scientists more generally. So our original concept, Ellie Armstrong and I, so she's from STS, we're thinking about this sort of issue of, are we as space scientists engaging with ethics and issues of social science as it relates to space? And are the scholars in those fields actually reaching space scientists, where there's a lot of two-way learning that can be had? And I think we were both a bit frustrated coming from opposite sides of these problems, about how to make that bridge. And we were just thinking, okay, UCL is offering a grant, let's apply and just see if we can get a mix of speakers across these disciplines to get together in one room. And it sort of blossomed from there because we thought, okay, it asked for tentative speakers. We put down our dream speakers, and then we thought we have to pay them enough, and we really, really want to focus on accessibility. So we're thinking about transcriptions and captions and signage and that sort of thing. And also had to think about renting rooms and finding accessible rooms. And then at some point we thought, what if we made it virtual and just saved on all those rental costs and really actually invested all this money in the people who can actually make this effective? And this was January.
That's prescient almost.
Yeah. We thought, I'm thinking back now, I don't think I was very confident in this whole virtual conference experiment, because we eventually spun it because we were worried, I think, to be a sort of, hey, we're interested in these topics, and the motivations here about bringing together disparate parts of academia. But we also want to experiment in how to make a virtual conference when we think about access, where I'm disabled and conferences are just a nightmare. And also the climate, where a lot of travel is done by academics for conferences. So we were just saying, we're going to try to derive as much best practice as possible from this experience. And if it catastrophically fails, that's a result. We can pass it on to the next people and say, this doesn't work for virtual meetings, whatever. So it was kind of a humble beginning. We just thought, this might be interesting to the folks at UCL. And we got our funding in about probably the 8th of March when everything was kicking off. And we thought, okay, this is very, very lucky. And I made a tweet about it, and it got all this attention. I thought, oh gosh, what have we got ourselves into? And so it's taken off from there. It's certainly still really focused on the subject matter, but I think a lot of people are interested in seeing how we do it, which is a lot of pressure, but really exciting. So the conference format is based on a flipped classroom model. So again, focusing on the access point of view, where we're thinking about people with caring responsibilities, and also the onus on speakers to do live presentations. So the idea is that our speakers and poster presenters will give us the material in advance. The speakers' videos will be transcribed and captioned by a company that we've involved. And then these media will be uploaded to our website a week in advance. And so all attendees can engage with all the material, think about it, research, use, or look at it the night before, which I'm sure many will. And then log on the day of the conference across 3 different sessions, which are spread out based on time zone availability of our speakers, and actually just talk to the speakers about what they've presented, and talk to each other and come up with ideas and brainstorm and spin off from there. So we're hopefully also having some breakout rooms where people can talk to other people about what they've just learned and discussed. And so we're really trying to simulate what gets lost in a virtual conference, which is the human interaction of things.
Yeah,
because,
exactly.
So, something that's really great about, say, recording this podcast right now is that we're having a dynamic conversation, right? And you can say what you just said and interact with me, and I feel affirmed, and we can bounce ideas off each other. Whereas I think in virtual presenting, it's very sterile and 2D even, right?
Yeah. Because ultimately, if you're just there presenting, what do you really get out of that? The whole point of conferences is the human interaction element. Exactly. It's not the sit down and watching talks. So yeah, so it's a really good idea.
Yeah. And it's something that we've seen emerge, I think, since all these conferences either moving virtual or canceling, is that a lot of people are saying, what happens to all the organic stuff that happens when I have a coffee with someone I've never spoken to, and then we come up with an idea, and that becomes our, a career trajectory, right? And all of that disappears. And I think we really wanted to focus on that with this subject matter, because we really wanted to bring together people, and having a static sort of video hosted on a website isn't the same thing as having a planetary scientist talk to a sociologist about space ethics. I mean, that's not going to happen unless you actually put those 2 people together. So that really is our focus, and so we're hoping it works. We'll see. So we're slowly getting our videos right now, and we're getting them transcribed, and we also kind of last minute added these poster presentation opportunities, where we'll have between sessions, they're about 2 hours between sessions, the posters will be online again ahead of time. Everyone will engage. So the poster presenters also don't have to present, which I think can be nerve-wracking. And then you can just talk to them about their ideas, talk about, where they're thinking their projects are going, anything else. We have a lot of space scientists who are interested in in sociology and social theory and in STS who do this work kind of on the side. And I think it's a really great opportunity for them to get feedback from scholars in these fields, and also from each other, and to develop new ideas. So that's the general model of our conference. It is kind of different from a lot of these conferences that kind of flipped virtual all of a sudden. And so we're hoping it works, and we're trying to really center access. So like during the conference, we'll make sure to type up any questions anyone has, or say aloud any questions that people have typed. We've collected people's preferences about what kind of experience they want, if they're going to be only video, if they're going to be only audio, if they're going to be only text, to try to figure out how best to accommodate them. So kind of really focusing on what we feel are the failings of in-person conferences, and also the needs of people right now in this really difficult existence that we are occupying.
Yeah, I love it. I mean, it sounds like amazing timing. Obviously, there's been, growing concern over the effect on the climate of people congregating in one location on the other side of the globe for 5 days and then all flying back to their home countries. And then, there's no excuse at the moment for not making it more accessible, because we are all just at home. It's so much more of a level playing field now, so it makes sense. And from my perspective, I was like, how timely is this? How did Divya and Ellie come up with this? It's just amazing timing. So yeah, I'm so excited to see what it's going to be like.
Thanks, we are too. Yeah.
Is registration still open if people want to join in?
Yeah.
Or
registration is open until 2 days before.
Okay.
So yeah, our website is spacescienceincontext.wordpress.com, and the registration form is linked right up front.
Brilliant. We'll put some of that information in the episode description if any of our listeners are interested in joining in.
Please come.
Fantastic. And also the topic as well is an absolutely fascinating one in terms of ethics. It's definitely a conversation that I don't think has really been had enough recently, and particularly with talk of going back to the moon more substantially in the next few decades. It's definitely going to be a really important topic of conversation to have, not just amongst academic forums, but also with the general public as well, I think.
Yeah, I think we were really finding it pressing, where we have such a rich history of scholarship in things like, the relationship between space exploration and colonialism and war and profit and that sort of thing. And then you have us space scientists who are just kind of removed from that. And a lot of us don't know that work is happening. That there are entire ethnographies of how rover teams function. Like, do we learn about that? And something that got me really engaged with space scientists as a kid was realizing that we don't learn about it in school. And so coming from this other side has been frustrating, but also kind of exciting, and thinking about like, this is definitely the time to make that bridge and really have us talk to each other, because space scientists are also talking about these problems. And coming up with solutions, and talking about things like Starlink and funding issues, and what does our work really mean in the context of society, and how is outreach ineffective, or how could it be made better? And that and there's so much work going in parallel, and we're not working together. And so hopefully it starts something. But
yeah, I hope so. I think it's going to be really important going forward. I suppose also it's a question of timing, isn't it? Because we're just at this cusp now where a lot of these technologies and these missions are having real impacts. Whereas I suppose 20 years ago, it was more sort of arbitrary. Well, that's some future problem to worry about. But I think now is the time we need to sit down and think about it properly. Fantastic.
Amazing. Well, unless we have some other questions, we could ask Divya our final question. So if you could be doing something else other than gazing over the beautiful terrains of Mars, either in academia or outside of academia, what would you want to do?
Oh, that's tough. I'm an annoying polymath. So I'm also a poet and a composer, and I'd love to just be one of those things full time. But I think aside from those passions, I think one of my sort of dreams in another universe is to be a behavioral ecologist and study wildcats.
Nice.
That is a very good answer.
Awesome.
Why wildcat in particular?
I don't know. something about them, just how they form complex relationships with each other and between different types of big cats, whether it's tigers or leopards. I think it's just really cool, especially coming from someone who studies, rocks that have been around for a couple billion years. It's, something a bit alive and exciting.
Yeah. To be fair, we ask this question to all our guests, and quite a few people do normally say something to do with living things, like plants or animals or something. Yeah. So I think, we are all secretly craving something that isn't just rock.
Non-inanimate objects. Yeah. Wow. That's a good answer. Brilliant. Well, Divya, thank you very much for coming onto our podcast. I hope the conference goes well.
Thank you.
Yeah, we'll be really interested. You should come back on at some point maybe and talk a bit more once the conference is done, because I think there's a lot more we could talk about ethics. That'd be quite an interesting conversation there. Mm-hmm. But anyway, yes, thank you very much. In the meantime, to all our listeners, thank you very much, and we'll see you again next week. If you want some more Earth and Solar System content, do check us out on social media everywhere, from the Facebooks to the Twitters to the Instagrams. We're at Earth Solar System. All the links will be in the episode description. But until then, stay safe. Thanks very much for listening, and see you all next week. Bye.
Bye.